Myself, Dr. Somir De, teacher in charge and assistant professor of mathematics section under Department of Basic Science and Humanities. This is lecture number 1 under module number 3 on topic vector space. Paper name is Mathematics 1A, paper code BSM-101, branch Computer Science. Vector space. Let F be a field, then a non-empty set V together with the operation plus V cross V to V and F cross V to a V is called a vector space over a field F if it is satisfies the following condition. So from here it is clear there are two operations you have. One is plus, another is dot. Okay, there are two operations V to V, V cross V to V and F cross V to F is called a vector space over a field F. It is satisfies the following conditions. Okay, number 1, U plus V plus U W is equals to U plus V plus W for all U V W belongs to V. U V are the elements of vector are empty set V. So from here it is clear that is a single operation you have. So already you know that if you have a single operation and then you can combine any two. Like here it is a UV and then it is a VW. Okay. Number 2, then there exists, this is just you can check, this is a bold, that is null vector of V such that U plus, that is U plus V, U plus null vector is equals to U is equals to null vector plus U for all U belongs to V. Clear? So this is most important property, that is a identity property. Then for each V, then each V belongs to V, there exists a U belongs to V such that U plus V is equals to null vector is equals to V plus U. This property is called inverse element property under addition operation. The element U is called the additive inverse. So under operation addition, so that's why this U is called additive inverse of V and it is denoted by minus V. So up to 1, 2, 3, these are all based on addition. Number 4, U plus V is equals to V plus U for all, that is a commutative property, under operation plus for all U V belongs to V. Number 5, A dot U plus V is equals to A dot U plus A dot V for all U V belongs to V and A belongs to F. This is called associative property. Okay, and left side operation AU A dot U plus A dot V. Number 6, A plus B dot U. So this is A plus B scalar. So A dot U plus B dot U for all U belongs to V and AB belongs to F. Multiply type AB dot U is equals to A dot U dot U. Okay, so already you know from the vector concept that operation always dot or cross, both parts should be a vector. Similarly for in this case, suppose B scalar B dot scalar dot the operation A dot B dot U. Okay, next number 8, 1 dot U is equals to U for all U belongs to V where One is the multiplicative identity of F. Okay. Some properties, most important property from vector space. Let F be a vector space over field F. Then we have the following: a 0 vector is equals to 0 for all a belongs to F. Number 2, 0 vector dot v vector is equals to null vector for all v belongs to V, and a v vector is equals to null imply either a is equals to 0 or v is a null vector. Number 4, minus a of v vector is equals to minus a v vector is equals to minus a into a minus v for all a belongs to F and v belongs to B. Okay, this in general, the particular case, if I put a is equals to 1, then you can see this one. Try to understand. Let a proof. It's a very easy property. You can see. Let a belongs to F, then a 0 vector is equals to a 0 plus 0 vector. So from here you may write from the previous properties, from the proper conditions, that is a 0 vector and plus a 0 vector gives. Ultimately, if I cancel, if I left cancellation law, then what is left? That is a 0 vector is equals to 0 vector. Okay. So first part is proof. Next, let V belongs to capital vector space of V, then 0 V is equals to 0 plus 0 V. So you can use the same operation, 0 V vector plus 0 V vector, left cancellation law. So from here it is clear that 0 V vector is equals to null vector. Next, number 3, let a b vector is equals to 0, and if a is equals to 0, then the result follows by 2. So from here, suppose a not equals to 0. If a not equals to 0, then so a inverse a v vector is equals to a a inverse a v is equals to 0, already you know from here vector. So ultimately this becomes this is possible, gives you a v is equals to 0 vector. This result is true for v is equals to 0 vector. Number 4, 0 vector is equals to a, 0 vector is equals to a, v and reverse of v, that is inverse element of v, that is v plus of minus v is equals to ab plus a minus b. Thus a minus v vector is equals to minus of a v vector. Similarly, a plus minus a, that is inverse of this element, v over 0 v is equals to 0 vector, null vector, gives minus a v vector is equals to minus a v vector. Subspace. A non-empty subset W of a vector space V over field F is called a subspace of V if W itself a vector space. If W itself a vector space over a field F with respect to operations on V. Non-empty sets null and V of V are subspace of V. Note that V is the largest subspace of V and 0 singleton set is the smallest subspace of V. So from here it is clear. Suppose first of all a set subset of vector space V. So if W itself a vector space with over F, then you can say W is a subspace of V. Now is some properties you should go through. A non-empty set subset W of a vector space V over F is a subspace if and only if W plus W1 plus W2 belongs to V, and AW belongs to V for all A belongs to F, and W1 W2 belongs to F. So if I come, this is another condition by which you can prove that that W is a subspace of V, as well as another property. If I combine these two, that is AW1 plus BW2 belongs to V, then we can say this also a subspace of V. So that means here you have to prove double condition. But if you combine these two, then you can write if I can try to understand, that is A W1 plus B W2 belongs to W. If yes, then you can say W is a subspace of V. So ultimately, if what you are doing, you are combining these two. Okay, so this is also possible. Now, if W be a subspace, then it itself a vector space. Therefore, for all A belongs to F, W1, W2 belongs to W. We have W1 plus W2 belongs to V, and AW belongs to V. Conversely, suppose that W1 plus W2 and AW belongs to V for all A belongs to F. Okay. W1, W2 belongs to W. Since W is a subset of V, hence it is immediately follows that W plus W1 plus W3 is equals to W1 plus W2 plus W3. Obvious property, that is AW1 plus W2 is equals to AW1 plus AW2. Similarly, A plus BW is equals to AW plus BW, and A W1 plus W2 is equals to W2 plus W1. Commutative property, 1 W is equals to W, AP W is equals to A BW. Here where A1 AB belongs to F, and W1 W2 W3 W1 W2 W2 W3 belongs to F. Since minus W is equals to minus 1 of W of B, so each W belongs to W. Hence, null vector W minus W belongs to capital W. So therefore, W is itself a vector space with respect to the operation of V. So this is the proof of this property. Another property, just like same second. So anyone, either you can substitute. Sometimes I will discuss with some example. You have a question, prove that this set is a subspace. So you can use this property or this one, anyone you can see. But according to me, so this is the easiest. No need to prove twice. In a single line, you can check. Provision number 2. A non-empty subset W is a subspace of vector space V over a field F if and only if AW1 plus ABW2 belongs to W. For all AB belongs to F, and W1, W2 belongs to W, capital W. If the capital W is a subspace of V, then it is a vector space by default, and so A W1 plus B W2 belongs to V, belongs to W for all A comma B belongs to F, and where this W1 and W2 belongs to W. Clear? Because W is a subset of V, so V is a vector space. So W automatically by default is a vector space. Okay. Conversely, suppose AW1 plus BW2 belongs to W for all A comma B belongs to F, and W1 comma W2 belongs to capital W. Take A is equals to B is equals to 1. We have W1 plus W2 belongs to V. So let A belongs to F and W belongs to W. then AW plus 0W belongs to W, but W belongs to capital W. There is a and W is a subset of this. So hence AW is equals to 0W, null W is equals to AW. So thus AW belongs to capital W. So this is by using property. So using proposition 1, so W is a subspace of W. So that means this property is coming from based proposition number 1. Sometimes you can see some theorem. So the intersection of any two subspace of a vector space is a subspace. Intersection of two subspace of a vector space is a subspace. Let W1, W2 be any two subspace of a vector space V over F. Then 0 belongs to W1 and W2, and hence 0 belongs to W1 intersection of W2. Thus W1 and W1 intersection W2 is non-empty subset of V. So our first condition is 1. Let AB belongs to F and UW belongs to W1 intersection of W2. So from here it is clear that UV belongs to W1 and UV belongs to W2. So since W2, so individually W1 and W2 be two subspace. So from here it is clear that is AU plus BW belongs to W1 as well as AU plus BW also belongs to W2. Okay. So therefore, so this part AU plus BW also belongs to W1 intersection W2. This shows that the W1 intersection W2 is a subspace. Okay, so this is also very important part, very easy. First you have to prove that it is a null, then that is non-empty, then prove. I repeat once again, let W1 W2 be to any subspace of a vector space V over F, and then null vector belongs to W1 and W2 because it is a subspace of this. So automatically this 0 null vector should belongs to this, and hence 0 belongs to W1 and intersection of W2. So that means if null vector belongs to W1 and W2, so same null vector must belongs to W1 intersection of W2. So that's why W1 intersection of W2 is a non-empty subspace of W. Let AB belongs to V. So now you are selecting U V vector belongs to W1 comma W2. So this means let you are considering that U and W belongs to W1 intersection of W2. It means UW belongs to W1 and UW belongs to W2. Clear? Since W1 and W2 is a subspace, so automatically this AW plus BW must be belongs to W1 as well as AU minus BW belongs to W2, because this is the condition that if it is a subspace then it must be satisfied. Okay, so from here it is clear AW and AU and BW belongs to W1 and W2. So you can say AW plus AU plus BW also belongs to W1 intersection of W2. This shows that W1 and W2 is a subspace. So this is also very important property. Now what type of question you can see from here, some theoretical question you can see from this, and now try to understand the question. Prove that let V be a vector space 3 cross R. This RQ means a real space with third order is a vector space over, then the W is equals to X comma Y belongs to R cube, satisfy X plus Y minus 2Z equals to 0, then so that W is a subspace of this. So already you know there are two conditions you have, that is either alpha W1 that is you can say alpha beta belongs to W, then A alpha belongs to W. Otherwise you can say A alpha plus B beta. We want to apply the second one. Let alpha is equals to x1 y1 z1 and beta is equals to x2 y2 z2 be any two vector in W, where x1 x2 y1 y2 z1 z2 belongs to R. So when this point is coming from here, so that means this x1 y1 z1 must be satisfied this relation, that is you have x1 plus y1 minus 2z1 equal to 0. This is number 1. So when you are considering beta from this, so that means this x2 y2 z2 must be satisfied this relation, that is x2 plus y2 minus 2z2 is equals to 0. Clear? Now what is your a alpha plus, now for any two real number a b we have a alpha plus b beta. A alpha means this a into x1 comma y1 comma z1 plus b x2 comma y2 comma z2. If I simply simplify this, what you have a x1 plus b x2 comma a y1 plus b y2 comma a z1 plus b z2. Clear? Now if we can prove that this coordinate satisfies this relation, we can say that W be a subspace of R cube. Let's see. Now you put this this coordinate into this relation, that is x1 plus b x2 plus a y1 plus b y2 minus 2 of, because this formula wise, 2 of a z1 minus a plus b z2. Now you take common a1 common x1 plus y1 minus 2z1 plus b common x2 plus y2 minus 2z2. Just to check from equation number 1 and from equation number 2, this equals to 0 and this equals to 0. So that means a into 0 plus b into 0 ultimately 0. So that means this coordinate, that is a alpha plus b beta, satisfies this relation. So that's why, so a alpha plus b beta belongs to W for any two vector alpha comma beta belongs to W, and any two constant a and b. So therefore W is equals to x y z belongs to R. Oh, sorry, some missing is a subspace, just typing error. So x plus y minus 2z equals to 0 is a subspace of R cube. Okay, now you check same type question, so that x y z belongs to R cube, 3x minus 2y plus z is equal to 0 is a subspace of R cube. Same way, let a alpha x1 y1 z1 and beta x2 y2 z2 be any two vector in S. Therefore x y z x1 y1 z1 x2 y2 z2 belongs to R. So according to when your alpha belongs to this set, that means this 3x1 minus 4xy1 plus z1 equals to 0. This is equation number 1, and then 3x2 plus minus 4y2 plus z2 equals to 0 from this relation. Now for any real number a b, we have a alpha plus b beta, that is a x1 y1 z1 plus b x2 y2 z2. If we simplify, what we have a x1 plus b x2 comma a y1 plus b y2 comma a z1 plus b z2. So if I simplify, there are three components you have. There are three components. If I add, there exists three components with addition. Now we want to check whether this a alpha plus b beta belongs to this S or not. What do? You have to just this coordinate should be satisfied this relation. Now you substitute here 3 a x1 plus b x2 is minus 4 a y1 plus b y2 plus a z1 plus b z2. If I take common a, what we get? 3x1 minus 4y1 plus z1 plus b, 3x2 minus 4y2 plus z2 is equals to a into 0 plus b into 0. Why? Because 3x1 from equation number 1, 3x1 minus 4y1 plus z1 equal to 0, 3x2 minus 4y2 plus z2 equals to 0. Okay, so therefore a alpha plus b beta, so it belongs to S. So therefore any vector a alpha and beta belongs to S. This is a just typing mistake. Any two real number a and b, for a and b, thus S x comma y comma z R cube a 3x minus 4y plus z equal to 0 is a subspace of R cube. So this type of question you can expect. Okay, thank you. Try to solve this type of question by yourself.